All right, so today's topic is password cracking. A lot of people is interested in this area because whenever they hear that I'm a cryptographer, they ask if I can capture some passwords. In theory, yes, you can always capture a password, but the approach sometimes changes between the hacker and the cryptographer here, because hacker generally tries to capture the plain text, capture the password, sometimes because it is kept as plain text, or sometimes it captures the hashes of these passwords so that they try to overcome this problem. So we are actually focusing on the second part, where we actually capture the password, but it is somehow masked using a hash function. So we are going to talk about how we should securely store a password. Actually, that is our main driving force here. So we talked about this before. We don't store the passwords as a plain text, but we store their hashes. Okay, this is important because the basic principle here is that if you store the user passwords in a file or in a database, most probably at some point it will leak. Every database leaks. You know, we have web pages where you hear stories and they store them, so that you hear one day that 500 million or 500,000 of Facebook users' account info are stolen, and so on and so forth. So when those breaches occur, if the passwords were stored as plain text, they would also leak. Okay, so whenever that data breaches occur, most of the time these companies say that your passwords are secure, don't worry, but you can change it if you want. So let's look at the idea behind it. Yeah, the leakage of database should not leak the passwords. Hence, the hash function should be preimage resistant. So here we are relying on the preimage resistance of hash functions. So if we use hash functions, assume that as the basic scenario, we have the password, and instead of storing the password, we simply calculate the hash of it and store it in the database. So it is the basic thing you can do, but you shouldn't do it in practice. But assume that this is what the people are doing, and people are actually doing this, by the way. So in those scenarios, you can always perform the dictionary attack or the exhaustive search attack. So this is unfortunately not how a dictionary attack works, and I'm not allowed to throw dictionaries to students, but this is how you do it. Okay, so assume the scenario where you capture the database, and when actually anybody captures a database, they announce it on the web, so you can download it and find the hashes of user passwords. Okay, so assume this simple scenario. So what you can do is as follows: before waiting this kind of a breach, so before having those hashes beforehand, you actually calculate. So in this scenario, we call pre-computation, because you don't have the database yet. You pre-compute the hashes of common words on a dictionary, their combination with numbers, special characters, and so on. So you create your own dictionary here and calculate the hashes of them. So assume that SHA-256 is the most favorite hash function today. So you calculate SHA-256 of all of these passwords. So maybe you created 1 terabyte of passwords. You calculate the hashes of these passwords. Again, assume that it is stored in a 1 terabyte. So you have a hard drive full of hashes of passwords. So you keep them sorted in a table. So you write it to the hard drive in a sorted way. The attacker can capture the passwords if their hash values are already in the table that they captured in the database. So you capture the database, you get the hashes, you sort them, you already have a sorted list, and you try to match them and see if any of them matches. So if any of them matches, you already know which password produces that hash value. So this is how a dictionary attack works. So in capture the flags, this is generally what you do. You know, you capture a file where you have the user's password in a hashed way. So you use generally tools like John the Ripper and so on. So you just capture the password. During those, you know, capture the flags and so on. So how we can overcome this problem? So idea is to use salts. So basic approach is that instead of storing the hash of a password, just store the hash of a password with the concatenation of salt to it. So salt is a randomly generated publicly known value. This is what we mean. For instance, when you go to Facebook and create an account, you choose your password. So you send your password to them. You are saying that this is my password. And at that time, they randomly generate a value. Generally, people use 32-bit random values. Of course, larger is better, but anything smaller than 32 bits will not be a good idea. So they append this salt to your password. So your password actually becomes something even longer, and calculate the hash of it and store it in the database. So whenever you want to log into the web page, you send your password to them. So in the database where your username, your salt actually appears there. So they use that value to calculate the hash and check if the hash matches the one in the database. So this is how actually you log in to any web page. So if you use salts, then the previous dictionary attack will not work, because now the attacker has to generate tables for every salt, which is not practical. Because beforehand, I cannot create a dictionary because I don't know your salt value. But assume that the salt is short, like 16 bits. Then when I create a dictionary like here, now I have to generate 2 to the 16 of them for every possible salt value. Of course, now this makes, if your dictionary is like a few gigabytes, now we are exceeding terabytes because you have to generate 2 to the 16 different dictionaries. So using salts actually prevents this kind of pre-computed dictionary attacks. But this doesn't solve our problem yet, because if you use salts like this and calculate the hash and store in the web page, when those hash values and salt values leak, now I can do a brute force attack. In other words, an exhaustive search where I'm searching the password. So when a hash and the salt value is obtained, calculate hash of every possible short password and check if the hashes are identical. Okay, so now this is not a pre-computed attack. Now I'm performing the attack in real time. But now it depends how many passwords I can try in a second. And if you have short password, then it will be easier to break. So let's look at how this works. And let's focus on 8-character passwords search, because most systems use 8-character passwords. Some doesn't allow you to choose something longer or shorter. Okay, so let's see if those approaches are safe. So English alphabet has 26 letters. If you use the capital letters, we get 52 characters. If we add numbers, we get 62 possibilities now. And there are actually 94 printable characters in ASCII. So these are actually the things that you can press with your keyboard buttons, okay? So assume that you chose a password, but it only contains like small letters from English alphabet. So in theory, you can choose at most 26 to the power 8 many passwords. So if you calculate this number, it becomes this. But we generally prefer to show it as the power of 2, because I will mention how easy or how hard it is. But here, assume that we are talking about using SHA-256. So you create the password, somebody appended a salt to it, and calculate the SHA-256 of it. So in the brute force attack, now I have to try this many SHA-256 computations. But modern GPUs almost can do this many operations in a second, okay? So 2 to the 34 or 35 operations, SHA-256 operations in a second, is not that hard for a modern GPU like RTX 4090. In the previous versions, you can calculate 2 to the 33 or 2 to the 34, depending on the GPU power of yours. But I'm talking about a single GPU here. If you have 1,000 GPUs, then your power increases by 1,000, okay? So choosing such a password is not secure. So this is why when you create a password, the web page says that also use a capital letter, So let's use a capital letter. But now the space increased to 52 to the power 8. As you can see, as the power of 2, it's reached to this. So assume I have a GPU that can perform 2 to the 35 SHA-256 operations in a second. This means that I have to use my GPU for 2 to the 10 seconds, which is 1024, right? So it is like 15 minutes or something. So from seconds, now you reach to the place where it takes more than 10 minutes, okay? So this is why they ask you to put a character number in it. Now the space increased, but as you can see, it is something like negligible. So this is why they also tell you to use a special character, right? So let's assume that I can use every possible printable characters in ASCII. Now the space is this, okay? So if you think about it, now I have to use my GPU 2 to the 17 seconds. So 2 to the 17 actually is not a huge number. I think it will take a few months. But the thing is that if you have thousands of GPUs, then you can do it in a few minutes anyway. And people have many GPUs, right? They have GPU farms, or you can even pay money to Amazon and use their GPUs or Google's, right? So this attack is easy. So this doesn't solve our problem too. And also we can search the space in a clever way. For example, users select easy to remember short passwords. They almost never use more than 2 special characters. I don't want to give more information because it's kind of exceeds the limits of being ethical, because now I'm actually going to tell you how people choose their passwords, but somebody has to say it. You know, if you force people to use capital letters, numbers, and special characters, what people are going to do, write a single capital letter, then small letters like a word, then a number, then a special character. So this space is actually very close to this one in general, in practice, okay? I'm sorry, but somebody had to say it, okay? So how do I overcome this problem? Because if this is the case, then this means that 80 character passwords are no longer secure, but we are always using this kind of password. So the countermeasure, which you cannot do, but the designer can do, is as follows. We can slow down the hash computation speed. This way, I can slow down the brute force attack because it will take longer to perform the brute force attack. So I did as follows. Instead of using the hash value of a password, repeatedly use the hash output as the hash input. So I have your password. I appended a salt to it. I considered this as an input to SHA-256, calculated the output, and instead of writing this hash value to the database, I again take it as the input and put it in the SHA-256, obtain a new output, put it again and again and again, okay? So, for instance, assume that I repeated this process 8,192 times. This was a default value in Linux a few years ago, but probably they increased it. This way, the attacker's job becomes 8,192 times harder, because instead of calculating a single SHA-256, when they try a password, they have to calculate SHA-256 this many times. So in the previous scenario, if I can capture your password in 1 day, now in this scenario, it will take more than 8,000 days for me to capture it. So this is how the slowdown works, okay? So if you're paranoid, you have to increase this number because, you know, devices are getting better. GPUs are really getting faster and faster because the number of cores are really increasing. I think now we have more than 10,000 cores on an RTX 4090. And all of these cores are at a very high clock speed, like 2.7 gigahertz or something. So these are really good speeds. But of course, you can always build an ASIC, which will be, you know, consuming less power than a GPU, but perform more SHA-256 operations. So this actually raises one question. In Bitcoin mining, we have ASICs which actually perform SHA-256 operations. So question is, can I use them to crack passwords? So in theory, you cannot, because in those devices, they say that we designed these devices so that it will not be usable for password cracking. They have to say it, because if you don't say it, you cannot export that device to other countries. Okay, but if you know the inner workings of that kind of device in Bitcoin mining, you have to calculate SHA-256 twice. So we say double hashing. So if you can somehow use that input and output as you want, so in that kind of device, you can divide this number by 2 and put that password as an input to that device. But again, everybody claims that you cannot use those devices for password cracking. But just know that look at the hashing capability of all of the Bitcoin miners in the world. And then this can give you an idea how many password tries they can perform. So I think this number actually is less than the hashing power of all of the ASICs in the world. So actually Bitcoin miners can capture such a password in less than a second, in actually milliseconds. So this is why don't just focus. And if you Google, you can ask if 8-character passwords are secure, and you will find blog posts or web pages where they are going to tell you that it is secure. And sometimes they even provide calculations. And in the calculations, you realize that an attacker can try 2 to the 20 passwords in a second, because those blog posts actually focus on CPUs, and they're old. Okay, this is why I'm saying that 2 to the 52, a secrecy agency can perform this many operations in less than a second. Okay, so don't rely on that. So increasing this number is important. Again, like 5 or 6 years ago, I looked at one of the Linux versions. I think this was the default value there, but you can manually change it. So actually, this is one of the important values in a config file nobody knows about. Okay, when you install Linux, just go, config file and increase this number if it is small like this. So in some examples, like password-based key derivation or WinRAR and so on, actually this number is large in WinRAR larger, but in password-based key derivation like WP, it is smaller. So it depends on the application. This is a choice by the designer, but this number looks small to me in 2022. Okay, choose something larger than 10,000. Okay.